Hello everyone, this is Dr. Abdul Pasha. Course is Power System Operation and Control. So here today we will discuss the topic named Economic Scheduling Analysis. So what is this Economic Scheduling Analysis? So far we discussed so many points regarding hydrothermal scheduling processes. So with this we are going to make certain assumptions to go with the economic scheduling analysis process. So here economic scheduling of power systems are also known as economic dispatch. So this is a process used in power system network to determine the most cost effective way to meet the electrical demand by distributing the generation among available power plants. So here the goal is to minimize the total operational costs while satisfying various constraints like power demand, transmission limits and generation limits. So these are the limits we are going to be considering. So here is a breakdown of the major components involved in economic scheduling process. So here the main objective of this economic load scheduling of electric power generation unit is to schedule the committed generating units outputs so as to meet the load demand at minimum operating cost, while satisfying all the units and system equality and inequality constraints. So we discussed about all these constraints in detail. That it will be categorized as equality constraints and inequality constraints. Equality constraints and inequality constraints. So coming to here, in economic scheduling analysis, a conventional power system network operates with many generating units with different capacities and objective functions. So however, it is very imperative to run the network with the minimum cost. So the cost minimization of the plant is possible to attain by the optimization techniques. So here we need to select suitable optimization techniques for suitable economic load dispatch problem. So the economic load dispatch is an optimization technique which gives an economical condition to the generation and distribution of the given network. So coming through this economic load dispatch, a power network can select the units of the power plants for supplying the power to the demand side while satisfying all the equality and inequality constraints. So there are many conventional approaches to resolve economic load scheduling problems like lambda iteration method, linear programming method and dynamic programming methods. So these are the methods which are suitable for giving solutions to the economic scheduling of power plants. So here we will discuss this case with suitable considerations. The first one is objective function. So what is this objective functioning means? Minimization of generation costs. So the primary objective here is in economic scheduling to minimize the total cost of generation. So which can be expressed as a sum of the cost functions of all the power plants which are to be involved. So each plant has its own cost function that is based on the factors like fuel cost, heat rate and operating efficiency. So these are the parameters which will define the objective function of the particular given power system network. If you go with the total cost consideration, it will be equals to summation NCIPA. So what are these variables here means, where Ci of Pi is the cost function of the ith generator. Cost function of the ith generator. Similarly, P suffix I is the power generated by the ith generator. P suffix I is the power generated by the ith generator. N is here total number of generators. N is capital N is the total number of generators case. Now coming to here, the cost function for each unit is often modeled as quadratic function. So how can we frame it? Means Ci of Pi cost function, that is equals to Ai plus Bi Pi plus Ci Pi square, where Ai, Bi and Ci are the cost coefficients specific to the generators. Here we will consider one of the constraints, that is economic scheduling is subjected to various constraints that we need to fulfill here or satisfy. So with the power balance equation or power balance constraint, the total power generated must equals to the total load demand plus any losses in the system. So that is summation n, that is I equals to 1 to n Pi, which is equals to total load plus its loss coefficients, that is losses. So generation limits here are each generator can only operate with its minimum and maximum output limits. That is minimum is about which is less than or equals to Pi less than or equals to P max, right? So during this range only it can be happen. Each generator can only operate within this range of minimal to maximum, that is Pi. So here transmission constraints are considered in some cases with the transmission line capacities that may limit the amount of power that can be sent from one area to the other area. So these are also very much important in transmission line constraints. That means their capacities may limit the amount of power that can send from one area to the another area case. Next approach is called lambda iteration method. So what happens in lambda iteration method means one common method for solving economic dispatch problem is the lambda iteration method. What happens here means this method adjusts the output of each generator, that is based on the marginal cost. So here the derivative of the cost function with respect to the power is considered. So until the power balance constraint is satisfied, it will going to be taken place. So the basic idea is to find a uniform marginal cost, that is lambda across all the generators, that is dci by dpi is equals to lambda. So this implies that each generator's marginal cost must be equal to the system-wide lambda value for the dispatch to be economically optimal. So likewise, lambda iteration method is going to be considered here in this analysis. Next factor is incorporating the losses. That means it is associated with penalty factor. So in practical systems, transmission losses must be considered. So these losses are generally a function of the power flow. So that means a penalty factor is introduced for each generator to account for the effect of the transmission losses. So the objective it will be then replied as dci by dpi equals to lambda, where f suffix I adjusts the marginal cost based on how much amount of loss is incurred by the generator, or how much of loss is obtained by the suitable generator. Next parameter is economic dispatch with renewable energy. So, with the increasing integration of renewable energy sources like wind and solar, economic dispatch has evolved to consider the variability and uncertainty of renewable generation. That means these sources typically have zero marginal cost. So their generation is preterized, but their intermittency introduces a latest challenges for balancing supply and demand case. Now coming to here another parameter, security constrained economic dispatch. So what is this security constrained economic dispatch means? In modern power systems, economic scheduling also takes into the account security constraints. So here security constraints ensures that in addition to minimizing the costs, the system remains stable and secure. So even in the event of contingencies like loss of the generator or transmission line, security constrained economic dispatch problem is considered. So here is a simple example that gives how it will be better explained for a given two generator cases. So it is mentioned here C1 of P1, that is 500 plus 8 P1 plus 0.04 P1 square. C2 of P2 is 400 plus 6 P2 plus 0.03 P2 square. So here are the two cost functions for a given two generators. Then the total load demand is given with a value of 800 megawatts. So the generation limits are existing from 100 less than or equals to P1 less than or equals to 500 megawatts and 100 less than or equals to P2 less than or equals to 500 megawatts. So the goal is here to find the optimal dispatch for P1 and P2. So that minimizes the total generation cost while satisfying the load demand case. So what are the solution steps involved here means formulate the objective function and constraints, use the lambda iteration method to balance the marginal cost of the two generators, solve for the dispatch quantities like P1 and P2. So here it is a procedure involved that is called step-by-step solution method. Here the main objective is to minimize the total cost. That is total cost equals to C1 of P1 plus C2 of P2. And coming to the power balancing constraint, the total power generated by both the generators must equals to the load demand. How can we equate means P1 plus P2 equals to load demand, that is equals to about 800 megawatts. And coming to the marginal cost functions, we need to calculate the derivative of each cost function to find the marginal values. So for example, if it is existing with generator 1, then it becomes a DC1 by dP1, which is equals to 8 plus 2 into 0.04 P1. And for generator 2, it is existing as DC2 by dP2, which is equals to 6 plus 2 into 0.03 P2, which is equals to 6 plus 0.06. Coming to equating marginal costs, in optimal dispatch, marginal cost for both the generators must be equal. That means DC1 by dP1 is equals to DC2 by dP. So writing the expression here, 8 plus 0.08 P1 equals to 6 plus 0.06 P2. Now substitute power balance constraint. In the fifth case, we need to substitute the power balance constraint. That is from P1 plus P2 equals to 800. We can express it as P2 equals to 800 minus P. So here we have the quotient P1 plus P2 is 800. So writing for P2 it becomes 800 minus this will comes to here. So when you equate these coefficients 8 plus 0.08 P1 equals to 6 plus 0.06 into 800 minus P1. So instead of 0.06 of P2 we should keep this one. P2 becomes 800 minus. Now solve for P1, expand and simplify the equation. That is 8 plus 0.08 P1 equals to 6 plus 48 minus 0.06 P1. That is 0.08 P1 plus 0.06 P1 equals to 46 minus 8. So simplifying for this, we may get 0.14 P1 equals to 38. So what is happening here means 0.08 P1 and 0.06. These two options will be added and you are getting a value of 0.14 P1. So here 48 is there and which will be subtracted from here and that is about 46 minus 8. And you may obtain 0.14 P1 equals to 38. So P1 equals to 38 by 0.1. So when you cancel each other, then you may obtain 271.43 megawatt. This is about only P1. And solving for P2 by with the help of P1. That is P1 is 271.43 megawatts into the power balance equation to find P2. And we have one of the expression that P2 is 800 minus P1. So by utilizing that condition, instead of P1, you should keep this 271 there. 800 minus 271.43 gives 528.57 megawatts. However, this violates the generation limits of P2 less than or equals to 500 megawatts per generator. So this means that the optimal solution must be constrained by P2, which is about 500 megawatts. And we need to adjust P1 accordingly. So after adjusting the constraint violation, we need to set P2 equals to 500 megawatts. So from the power balance constraint, P1 equals to 800 minus 5. This is about to 300 megawatts. So with this, the final dispatch is considered to be 300 as P1 and P2 is 500 megawatts. So when you adding these two, P1 plus P2, usually we have P1 300, P2 500. So both the combinations will resultants to you 800 megawatts. P1 plus P2 is 800 megawatts. So these are individual cases of P1 and P2s. Now total cost, let's we calculate the total cost using the cost function. Cost for generator 1, that is C1 of 300, 500 plus we have 8 into P1, that is 8 into 300, 0.04 P1 square. P1 square means 300 square. So this becomes 500 plus 8 3 are 2400. Here 0 here it make this as square and multiply 0.04 into 90,000. So this gives a final sum value 500 plus 2400 plus 3600. 6500 you may obtain. Similarly, cost for generator 2 as C2 of 500. So by knowing the values of P2, 400 plus 6 into P2, 0.03 into 500 square, that is 400 plus 3000 plus 0.03 of 25, 2 lakhs 5000. So when you adding these two coefficients, then you may get 10,900. So now total generation cost becomes C total equals to C1 of 300 plus C2 of 500, which is equals to 6500 plus 10,900. So this total summation is equivalent to 17,400. So thus the minimal total generation cost is $17,400, which is the cost of total generation. Here we have the coefficients of P1 as 300 megawatts, P2 as 500 megawatts. Another analysis is mentioned here, given two bus system shown here. It is observed that when a power of 75 megawatts is imported to bus 1, so losses are amounted to 5 megawatts. Find the generation needed from each plant and also the power received by the load. The system lambda is given by 20 rupees per megawatt. And the incremental fuel cost at the two plants are given by, so here 200 megawatts, this is 75 megawatts. Load is connected at bus 1. Load is connected at bus. This is the line that should be connected. So with this, the functions of incremental costs are given. DC1 of P1 by DP1 equals to 0.03 P1 plus 15 rupees per megawatt. Similarly, DC2 of P2 by DP2 equals to 0.05 P2 plus 18 rupees per megawatt. Now the load is at bus 1, hence P1 will not have any effect on the line losses. Therefore, B11 coefficients are equal to B212 coefficients are equal to B210. This is because P1 will not have any effect on the line. So due to this, all the load coefficient, loss coefficients becomes 0. Now the loss coefficient can be represented as PL, that is BT2 P2 square. So when you substitute for here with this, then P2 value we already have. So P2 is 75 megawatts. Substitute here, and power loss coefficient is about 5. That you substitute here, and drawing for B22. So this becomes 5 by 75 square, 5650. That you need to substitute. Finally, B22 is 8.9 into 10 power minus. Now at the first power station, that is at station 1, C1 of P1 by dP1 plus lambda dou PL by dP1 gives lambda, and dou PL by dou P1 equals to 0.03 P1 plus 15 plus lambda, that is equals to one of the lambda constant. This is represented with equation 1. At station 2, similarly, dou PL by dou PT equals to 2B2 2P2. This will be dC2 of P2 by dP2 plus lambda dou PL by dou P2 equals to one of the lambda. So 0.05 P2 plus 18 plus lambda of 2 of 8.9 into 10 power minus 4 into P2 gives one of the coefficient lambda. This may be written as expression 2. So at lambda equals to 20 from the first expression, 0.03 P1 plus 15 equals to 20. Here 0.03 P1 equals to, when you shift here, 20 minus 50, which gives about 5. So under P1 case, that can be 5 by 0.03, which is about 166.67 megawatts. Again, from the equation 2, we have equation 2 in terms of 0.05 P2 plus 18 plus 20 into 2 into 8.9 into 10 power minus 4 into P2. That is 20. And again, if you rewrite this expression, 0.05 P2 plus 0.0356 P2 is equals to 20 minus 18. That is 2. So here 0.0856 P2 equals to 2. P2 equals to 23.3644 megawatts. So now total transmission loss as B22 P2 square. That is 8.9 into 10 power minus 4 into 23.3644 square, which is 0.4858 megawatts. Now the load demand at bus 1 is 166.67 plus 23.3644 into 0.4858. So this total sum gives a value of 178.02 megawatts. Now coming to this economic scheduling analysis, just now we discussed so many examples how the scheduling is divided and the power plant cost will be minimized with the minimal losses, and this can be extended to the economic operation in a fundamental problem of power system network, and particularly with the introduction of deregulations. So the deregulations of the power system network or reconstructing or restructuring of the electricity industry has become extremely essential. So this is to operate the power plants most economical. So the operating cost will be reduced with the reduced losses of the network. So it not only minimizes the cost per megawatt generation but also maximizes the social benefits. So, in general, the purpose of economic scheduling or dispatch is to determine the all the times of the cases. That means optimum combination of generation units are connected to the system. So, this is as to supply the load demand at a minimum cost. So, due to which economic scheduling problem consists of two separate cases of the problems involved. One is the first that is normally termed as unit commitments. We already discussed unit commitment. Um, that means meeting the load requirements. That means equal amounts of power sharing to the loads. As the demand, even though increases, it will be very ready and it will be very hurry to supply the power at suitable conditions. It may happen in daily cases or it may be in the night cases. So during this instance, the power demand may be varies. That's why the unit commitment problem is mostly introduced to meet the load requirement. So that is involved with unit commitments fees. And the second one is with online economic dispatch. So this will displace the lower demand to the generators which are fed. So according to that considerations of unit commitment and economic load dispatch problems, it will be very easily and necessarily can supply the power to the various loads which are connected to the respective generators. Even though the generator fails to supply the power to the respective loads, then any one of the generators they will be auxiliary connected to the system and they immediately react to the load requirement conditions and they will supply the power to the needed load demanded cases. So here the significance of the load schedules are must considered in modern power system. So load schedules are playing a vital role for modern power system networks. They helps in managing energy usages and costs. So especially in India, it will be happening. So by understanding and using these schedules, we can make our electric grid more stronger and more responsive to the nature. So here defining the load schedules and their roles in electrical systems plays a key role. That is for load schedules which will outlines how to manage electricity. So they are very essential for everyday energy usage and during high demand peaks. So statistics shows that 30 to 40% of energy goes to homes as a worldwide. And this highlights the need for efficient load scheduling to save energy and the money. So technology and changing energy usage have shaped load scheduling processes. For example, battery energy storage systems. They will play key role nowadays. All the vehicles they runs with the battery energy storage systems called by the name BESS. So which will helps to saves the energy cost. So they charge at night when their demand is low and supplies the power during the requirement condition. That means peak times. So this helps in stabilizing the prices and manage the energy efficiently and better. So here the impact of load scheduling on equipment sizing and power system studies also introduces in economic scheduling process. Here it will be considered with accurate load schedules which are crucial for power system studies and choosing the right equipment. So they helps to ensure the system reliable and effective. So sorting appliances by their energy usage is a key part of this process. So Fancy Energy focuses on affordable energy solutions. So it understands how important load scheduling is. So especially with the changes like the global pandemic situations, with the demand response programs which are more popular as people try to avoid high tariffs during peak hours. So this increases in consumer involvement supports Fancy Energy's push for sustainable energy. So the company's work in load planning helps to prepare for a future with more home-based energy production. So this is playing a very vital role for creating power system networks that can handle new challenges. So, in the conclusion, Fancy Energy knows that good load scheduling is the key to efficient and sustainable power system. So, as electricity demand grows more, especially in India, having detailed load schedules it is essential. So, this approach is both as a practical need and an economic strength. So likewise, the scheduling processes are plays very key role. That means developing an effective load schedule since 1938, the approach to managing loads has changed a lot. So by 1958 onwards, the use of ripple control systems are introduced as a common parameter. So Fancy Energy uses this long history to make sure their load scheduling is done. So this is the key for doing well in today's energy sector. Now, one of the methodology for creating accurate load schedules that will be introduced as creating a good load schedule begins with listing all equipment and their load ratings. So this helps to predict both regular and peak power needs. So adding the power factor ratings and how efficient equipment helps in making the things more accurate. So this builds on the work of the Theodore Prakash Bose in 1970. Whether a load is constant, intermittent, or backup, and its levels are important at the core of the Fancy Energy's planning process. And considerations for classifying loads by critically and optimal. That is, classifying the load is crucial. So it's more than just organizing, it's central to scheduling ripple control technology that will be needed to classify the loads for better action plans during the load sheds and to avoid blackouts. So knowing the type of the loads helps with both daily scheduling and emergency. One of the tools and techniques for load planning in divergence settings are introduced. So, in today's environments, advanced load planning tools are needed. So, power logging and programs like Microsoft Excel are in key, making electrical load schedules. So, history has shown that using specific templates can cut down work time. This shows progress in methods and how tools helps in scheduling process. So standards like Philippine Electrical Code and Excel Solver make sure load planning is both optimized and following the rules. So with this, the scheduling process can easily be matched for the given load. So these are some of the references that I have taken. So which will be very useful in going through the course. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.